I want to continue our discussion on Recon and pivot from active scanning over to the concept of OS fingerprinting or operating system fingerprinting. Now, OS fingerprinting is really a series of techniques that allow you to discover what operating system a specific host is running. And when I say you, that can, again, be you pretending to be an attacker, or it can be an actual attacker out there somewhere who's trying to break into your network, either from the outside in or once they're in the network during kind of that post-initial foothold stage. And there are a number of reasons an attacker might want to know the operating system of a specific host. First and foremost, if they're developing some type of exploit for that system, generally that exploit is going to need to be written specifically for a specific operating system. Without getting into the nitty-gritty of how exploits are developed, you have to change around a few different variables based upon the stack you're dancing around in when you're sending exploits, heap sprays, things like that over to specific hosts. So you have to know what that operating system is, oftentimes down to the actual service pack level, for instance, if we're talking about a Windows host. You also, as an attacker, need to be better prepared for post-exploitation activities. So once you've compromised a system and have access to it, you may need to deploy some additional software on that system, maybe a backdoor, maybe a rootkit. And when you do things like install rootkits, you really want to be careful to install the right architecture software, or you might crash the system or have some other adverse effect which actually ruins access as an attacker. And beyond that, you just really need to know where critical files are located. Various versions of Windows, various versions of Linux, and so on, they're going to put sensitive files that you may need to access in different places. So as an attacker, those are things that people are going to be concerned about. So it's important to be able to fingerprint what operating system is in use on a particular host that's being interacted with. Now, there are two primary techniques for OS fingerprinting, or at least two classifications of techniques with several different strategies within those different classifications. The first is passive OS fingerprinting, and that's where you look at data that you've passively captured, often via packet analysis, to make a judgment about what operating system generated those packets. There's also the active method, and this is where you're actually sending data to a system and observing the response. So you're generating very specific stimuli and observing the responses that come back, and based upon variance in those responses and what those look like, you can make a somewhat accurate guess about what operating system you're dealing with. So these are both valid techniques. Obviously, the passive technique is one where you have some mechanism to capture traffic that's a little quieter on the wire. You're not generating your own traffic. And active is a lot more noisy. So there are scenarios in which both of those might be beneficial. But we're going to go through some examples of each of those now and talk about why those things are possible and what it is about networking and protocols that allows us to do OS fingerprinting both in a passive and in an active way. Here's another slide we looked at earlier when we talked about IPv4 and specifically the TTL or time to live field. And you may remember the time to live field is really used to identify the number of hops or routers in most cases that a packet can traverse before it's dropped. And that way, if a packet gets stuck in a routing loop somewhere, it will eventually expire and report back to the user via some type of ICMP message, usually that the packet has been dropped and did not reach its final destination. Now, the TTL field is interesting because remember, it's a field value within the IP protocol. It's at IP8. It is just a simple 1-byte field, so it has a numeric value. So when I am on a Windows system and I generate a packet that's sent out, it's an IP packet, Windows chooses a TTL value for that packet, the initial TTL. And we've seen various examples of that. You've seen the example 64, 128, 255, etc. That number can be up to 255 since it's a 1-byte field. Now, the question I would ask you is, how is that initial TTL value set? What defines that? And you might say, well, it's probably defined in the RFC, the standard for the IPv4 protocol. And that is actually not true. It's actually not defined at all. There's not a specific initial TTL value that systems are supposed to have. It's one of those ambiguities that was left out of the IPv4 protocol spec. And there's nothing wrong with that. But the interesting thing is this leaves it up to the operating system developer or the stack developer to determine what initial TTL value they want to use. And of course, they don't all choose the same thing. And what that allows us to do is make judgments about the operating system that sent the packet, right? So if I see a packet with an initial TTL value of 128, I know it was probably sent from a Windows system. If it has an initial TTL value of 64, I know it was probably sent from a Unix-based system, just based upon general trends. And of course, it depends on the side you're receiving the data from, right? If you're on the transmitter side, you probably know what it's sent from anyway. But if you're getting it on the receiver side, and let's say the TTL value of the received packet is, 118. Well, if it's 118, you probably know that it was maybe 128 initially, and it just went through 10 hops to get to you. So you can make some educated guesses there, but I'll introduce this example just to demonstrate how it is these ambiguities, these unclear things in the protocol specs that leave protocol implementation open to interpretation. And that interpretation amongst different operating systems is one way you can simply look at a passively collected packet and maybe make an educated guess about what the device that sent that packet is. So I just went through this example. It shows how I can receive an IPv4 packet, look at that, and probably guess if it was sent originally from Windows or a Linux system. Now, that said, there are a lot of these different gotchas, these different fields that have these very specific initial values or initial settings within the protocol header. So it's not really a good practice to rely on one of those. TTL has been one of the stronger ones I found and one I often use, but there are a whole series of those. So I actually just want to go through a couple of those with you. Here's a chart that shows a few protocols and fields and what their values might map to under most normal circumstances. So you see right here at the top, we have the IPTTL value, which I've talked about and just talked about in the previous example. So a value of 64 is most commonly associated with Linux, Nmap, the network scanner, BSD, or OS X. A value of 128 is commonly associated with Windows platforms, and a value of 255 is commonly associated with Cisco iOS or Solaris platforms. So based upon those values, you can make a generalized judgment about what may have sent those things. Another field is the don't fragment flag and whether it is set by default or not, specifically when there are maybe no fragments in place. So Linux, Windows, OS X, BSD, and Solaris will set that value by default, whereas Nmap and Cisco will not. Another option is moving to the TCP header, the maximum segment size value. A value of 0, generally something we see with Nmap scanning, a value between 1440 and 1460 associated with Windows, and a value of 1460 specifically associated with Linux, OS X, BSD, and Solaris. So you see there's a little bit of overlap there. The value of 1460 could mean Windows, it could mean Linux, OS X, and so on. So a little bit of ambiguity there, but something that you can draw a little bit of a conclusion from. A couple more fields, TCP window size associated with a few options, a few different operating systems and platforms. So we see Nmap generally has a window size between 1024 and 4096. OS X and BSD have a very large window size, maximum size value they can have. Solaris 24820, and Windows is entirely variable. So you can't always make a sound judgment about whether a packet was sent from a Windows system just looking at the window size field. You have to rely on a couple of different things. Finally, we have the TCP selective acknowledgement flag and whether it's set or not set by default. In this case, we see Windows, Linux, OS X, OpenBSD generally set that by default, whereas Nmap, FreeBSD, and Cisco iOS generally have that not set by default. So we just went through 5 fields here, just a few different options to look at. There are actually quite a few more of these. If you have the Practical Packet Analysis book, this chart is actually in the book. I will also try to add this as supplementary material for the course so you can download that chart separately. One thing I actually have in my office right now is SANS, for the longest time, had a mouse pad that had a bunch of passive OS fingerprinting fields and common values associated with it. And I actually still have it in my office. It's completely filthy, and I probably shouldn't be using it anymore. But it's pretty darn handy to have that right at your fingertips. So even if you don't have the mouse pad, you might consider printing this off if you're doing this type of work commonly, and you have to do passive OS fingerprinting as a part of your job. I've opened a file called passiveosfingerprinting.pcap.ng, and I think it's a good example here because we have a simple bit of communication occurring between 2 hosts here, and I want to actually dig into each one of these and compare them and see if we can use what we learned about passive OS fingerprinting to learn a little bit more about them. So what I'm going to do in this case, I'm going to go ahead and just click on this first packet, and let's go ahead and say show packet in a new window. We're going to do it for the first packet, and let's go ahead and do that for the second packet as well. And let's go ahead and try to arrange these things where they're a little bit easier to see. We can get them both on the screen at the same time and do a little bit of analysis here between the two packets. I find this is a nice little way just to get a couple packets on the screen at a time when you actually need to see the packet details window. So I'm going to go ahead and shrink the packet bytes window. We don't need that. Try to get these as close to even as I can for our analysis. And okay, there we go. We should be good to go, and we can kind of compare these things holistically. Packet 1 on the left, packet 2 on the right. Let's start by looking at the, let's go to the TCP protocol. We'll start by looking at those first and kind of work our way down in this case. So let's go ahead and look at our options here, and let's see if the selective acknowledgement feature is enabled. And sure enough, it looks like it is on both of them. So TCP SAC permitted option, true here as well. That is the default value for Linux, Windows, OS X, and OpenBSD hosts. So we could probably surmise that we've limited our communication down to at least those 4 types of devices: Linux, Windows, OS X, and OpenBSD. Now let's go ahead and look at some other values. Let's look at the window size value in the TCP header. We see on this host, host 1, it is 64,240 in this case. We don't have anything in the chart I showed that maps to that, which might lead us to believe maybe it's a Windows host because it means it's variable to some degree. Over here we have a window size value of 2920, which is really low. That means it could maybe be Nmap, or it could also be Windows or Linux as well. Remember, that's also a variable field there as well. So that's a couple things in the TCP options we can look at. We can also look at maximum segment size. Here we see maximum segment size of this one is 1440, which means it's probably a Windows host. That's usually between 1440 and 1460. And then over here, we see the maximum segment size is 1460 bytes. Now, in this case, 1460 could be a lot of things. It could be Windows, BSD, OS X, Linux, Solaris, what have you. So a few more options over here, although the one on the left is really starting to look like it may be a Windows box. And if we go ahead and let's go ahead and collapse the TCP options here and look at IP. And the field I really look at often, the one that I find is the most often to accurate, is the TTL field here. And we see that we have a TTL of 128 for our system 1 in packet 1, and that generally tells us we've probably got a Windows machine. And over here we have a TTL of 64, which generally maps to either Nmap, BSD, OS X, or Linux. So if you were keeping track of all that, writing all that down, keeping a little chart and comparing it to what we've talked about, I think the conclusion you're probably going to get to is that packet 1 was generated from a Windows device, and packet 2 is probably generated from a Linux device. Of course, we don't know what flavor of Linux, Ubuntu, Red Hat, SUSE, whatever. We don't know, but it's probably a Linux device here on packet 2. So we have communication occurring between these two devices. So that tells us a little bit, helps us fingerprint the operating system on a passive level. And the beautiful part of this is we didn't actually have to send any packets on the wire. We just happened to collect some traffic between these two machines passively, and that's a nice clean way to do this. Helpful in your own analysis. I like to know often if I'm dealing with a Windows or a Linux box, especially if it's a network I'm responsible for, because then I can maybe start to figure out what the role of that system is. If I don't have a way to look that up really quickly, that certainly helps. So if I can see it's a Windows box and it's receiving data on port 53, I may know it's one of my Windows DNS servers. Maybe that DNS service is installed on a domain controller, and I can look for domain controller related ports open as well. So useful technique for the defender, obviously useful for the attacker as well, so you can figure out all the things we talked about earlier. But this is just a quick example of some OS fingerprinting, and you want to make sure that if you're doing passive OS fingerprinting, you take a look at the labs too. I have a couple lab exercises where you can practice this on your own. Before we leave passive OS fingerprinting behind completely, I do want to mention PRADS, because PRADS is a pretty neat tool. I believe it stands for Passive Recon Asset Detection System, and PRADS allows you to automate some of the things we've talked about. So essentially we just talked about like rules or heuristics, right? It said that if this value equals within this range, then it's probably Windows. It's just a series of those types of rules. So if you can codify those rules and put them into code, you can build an automated asset detection system, and that's exactly what PRADS is. It reviews packet data, and it looks at specific IP addresses, looks at the packet data for certain fields, and determines what it thinks the host that sent that data particularly is. And we have an output of that on the screen. Now, this isn't direct PRADS output. PRADS is a command line tool, but we have that installed here into the Security Onion distribution, and this is a transcript from Squeal, which is an IDS console. So someone has pulled up Squeal, and there's an integration between Squeal and PRADS, and you notice where the arrow is pointing there, the orange arrow. It says OS Fingerprint for 192.168.3.35, and it thinks it is Windows XP Service Pack 1 or 2000 Service Pack 3. So this is a little bit of an older screenshot, obviously, but PRADS is integrating that data into your intrusion detection analysis console, which is a pretty neat thing for a defender, is to be able to profile these machines live. You don't have to run PRADS separately. It's built into the tool. So there are a lot of tools out there, both free and commercial solutions, that will use PRADS or something like it to integrate this data into the analysis and provide that to the person doing the investigation. So check out PRADS. It's a pretty cool tool. You can download it independently and just run it. You can also download the Security Onion network security monitoring distribution, and it's built into that, and then you can take advantage of this integration as well. So if you're interested in learning more about passive asset detection using passive OS fingerprinting, definitely check out PRADS. I want to talk now about active OS fingerprinting. And active OS fingerprinting is very similar in concept to passive OS fingerprinting, in that we're looking for anomalies in the way different operating system vendors and manufacturers implement certain features of standard protocol specs. But the difference is, with passive OS fingerprinting, we're just listening to and looking at and examining data that we've already captured passively on the wire. And so we can only look at specific values that are set during normal communication sequences. With active OS fingerprinting, it's a little bit different. It's a little bit noisier because we're actually generating traffic on the wire. We're actually generating packets with a very specific stimulus, so we can observe the response we get back to those stimuli. And those stimuli are often very odd things you would not necessarily see in standard TCP/IP communication, because they're kind of gotchas, weird things that don't necessarily make sense. We talked about some of those, like Christmas tree scans and null scans and things like that, that will generate very different responses for different operating systems, and it is those differences that allows us to determine what the operating system of a particular host is. So I have an old slide on the screen here showing sequence and acknowledgement numbers, which we talked about a couple times for TCP. And what I would pose to you here is, okay, a system has to generate a sequence number when it initiates a connection to another system. How does it choose that sequence number? Furthermore, how does it choose sequence numbers between multiple connections? So if I do one connection to a host and then another connection a minute later, how do I choose those sequence numbers? Well, that's an interesting thing, and that's going to be different per operating system, especially across platforms like Windows, Linux, or OS X. So what you can actually do is collect a bunch of initial SYN packets that were sent in a connection, or even the SYNACs that are sent back, and do some math and basically come up with a decent idea of maybe what operating system sent those, or at least what operating system family sent those, so Windows, Linux, etc. So this is an example of active OS fingerprinting, and you'll find that these active OS fingerprinting techniques are a little bit more advanced. It's a little bit more complicated than what field value is set. It often requires collecting a lot of responses, or maybe even sending a lot of very unique packets and comparing responses across all those packets and generating something quite a bit more complex. Because of that complexity, generally you're going to use some type of specific tool to do your active OS fingerprinting, and that's what I have on the screen here. Is I have an example of how Nmap, the network scanning tool we've talked about a few times already, does active OS fingerprinting. On the right side of the screen, you see a list of a bunch of different tests it does. This is not all of them, but this is several of them. And you see that we have a lot more complexity. We have a lot of math going on. We have a lot of measurements of different responses from very specific stimuli and so on. So Nmap actually conducts all of these tests. When you tell it to OS fingerprint a device, it does all these things. It generates quite a bit of noise, a lot of traffic, and it records all the responses it receives from every specific test. And that's what you actually see on the left side of the screen. All that stuff that looks like nonsense is actually what Nmap calls an OS fingerprint or a fingerprint of a particular OS that it's scanned. So it will take all these values and it will actually compare those to its database of values and give you an approximation of what it thinks the operating system is. And the cool thing about this is it can get pretty darn accurate down to the service pack level with some degree of certainty if you're willing to sacrifice and send out all these packets and be really noisy. You may want to do that if it's just for your own internal purposes. An attacker may not want to do that because it's really going to light up, in many cases, intrusion detection systems that may lie on a specific system or that the packets have to cross to get to a specific system. So the right side, again, is the list of many tests that Nmap will run. The left side is an example of the fingerprint it will build based upon the results of those tests. Once it completes its run, it will generate output that looks somewhat like this. And this is, again, just a screenshot that ran against a bunch of honeypots. And you'll see here at the top, host 192.168.231.128 is running Windows Server 2003, Server Standard Edition, and we're 100% sure. So Nmap will also give you a percentage what it thinks its accuracy is. Everything on the screen here, it says 100%. Oftentimes, you'll get much lower percentages than that, but in this case, these were all 100%. We have an array of Windows 2003 server systems, Windows 2000 workstations, Windows XP, etc., a lot of different things. So Nmap, pretty darn accurate when you let it run the full gamut of tests. Again, though, if you're an attacker or pretending to be one as part of a penetration test, you want to be a little careful about running that if you're concerned about being caught, because many antivirus systems, host-based intrusion detection and network intrusion-based detection systems will flag and light up like a Christmas tree when it sees these very specifically formatted types of packets coming through because it knows it's involved in OS fingerprinting. That said, if you want to learn more about OS fingerprinting, really I think the best documentation for the active version is Nmap's documentation. So you can go to nmap.org. They have basically an online book that has their help manual pages and a lot of examples of OS fingerprinting. All the screenshots from this are from that specific documentation. You can actually dig into each one of those individual tests, learn more about them, learn more about that complexity. And of course, you can download Nmap yourself, run it on your own. You can download that, install that independently. You can download that as a part of the Kali Linux penetration testing distribution, run it straight from there. That works really great too. But that's the place I would go to learn more about that. I've also included a packet capture of active OS fingerprinting conducted from Nmap. It's called, not surprisingly, activeosfingerprinting.pcapng. We're not going to go through it here, but I want you to feel free to go in and dig around and play around with that. There are a lot of very odd-looking packets and things that would be very confusing to see in normal communication there. But definitely take a chance, go around and play with that as you end our module here on Recon and OS fingerprinting.